So could you please tell us about who you are?
Yeah, so my name is Emilio Botero. I'm a postdoctoral scholar at Stanford University, and I work in the aerospace design lab with Professor Juan Alonso.
Mhm. And why did you want to become an aerospace engineer?
So I actually never wanted to be one, which is probably one of the weird examples in all of your series. So I am really just like an aviation person. I like airplanes. My grandfather was a pilot. I grew up flying RC airplanes. And so I actually enrolled in Embry-Riddle Aeronautical University, and I wanted to become a pilot. Um, and when I got to school, I was flying. I was having a lot of fun. The classes were okay. And I was flying RC planes a lot. So a lot of my best friends were all in the RC club. And on the weekends, we used to fly RC planes together. And so actually, like talking to my friends and hanging out with them, they just convinced me, like, hey, if you're having, that those classes aren't that fun, you could come join us and take the classes that we're taking. And convinced me to become an engineer. So it wasn't really a planned thing. I didn't apply to be an engineer. I didn't plan this out in high school. It was just something I fell into. So that was definitely very different than probably most folks that you'll interview here. I never had any sort of, I'm not the typical engineering track. I didn't study really hard in high school with math and physics. I just very confident in aerospace kind of topics and really like the subject. So.
Mhm. And what aspect of aircraft design are you studying?
So I don't study necessarily one aspect of aircraft design. So aircraft design is a very general field. So to design aircraft, you need to be able to handle all the different systems, right? So you have wings, you have the tails, you have fuselages, and in those you have a lot of subcomponents, and they all have to interact and work together. And that's a very difficult problem to handle because everything has to be in balance. Unlike a lot of other applications like in mechanical engineering or civil engineering where things are on the ground, weight's not a constraint. And you can kind of get away with things that in an airplane you wouldn't be able to get away with because things are heavy and complicated. There's a lot of moving parts. And so in an airplane, we have to consider the whole. We have to consider all the different pieces and how they interact. So because of that, that requires my expertise to be quite broad. So more so than, I'm not really considering myself a specialist in anything. I'm really more of a generalist. I'm able to handle aerodynamics. I can handle structures. I can handle weight estimation, controls and stability. A lot of electrical engineering now, especially with electric airplane coming through. So there's a lot of different things that you need to understand in aircraft design, and then as well as how do you design, right? Because you can understand all those fields, but how do you go through the process of design? How do you actually come up with a vehicle that works, and how do you make something that is realizable? How do you optimize it? So there's a lot of different aspects of this, and it's both a depth and breadth. So you need to have some key areas. So for example, understanding the design process and understanding optimization, but you also need that breadth to understand how aerodynamics affects structures and how that affects the control of the aircraft, and how these all interact and how maybe some of the mechanical systems work as well.
Mhm. What is multi-fidelity optimization, and what is the significance in aerospace engineering?
Yeah, so let's start with what a fidelity is. So a fidelity is what we consider like a set of analyses. And let's give an example. This is the most basic example that most engineers would give you for aerospace engineers, at least for levels of fidelity. So in aerodynamics, we can do a really simple aerodynamic model that can simulate how the aircraft will behave. Maybe how much lift it will create at a certain altitude, at a certain speed and angle of attack, and we can say, hey, this airplane is going to get this. We'll have a very simple model, and that simple model might just be like a straight line, and we'll just say, hey, that's the straight line that's going to model how the lift is going to be at those conditions. But that's not really realistic, right? I mean, you're in high school, and a lot of folks here, they can just intuit, their intuition will tell them that's not 100% there. Maybe it's close though, but it's probably close enough for a lot of applications. So that's a low level of fidelity. Now we can go higher in fidelity. We can start running computational fluid dynamics, which is a process where we discretize the vehicle into like little chunks, and we analyze those chunks, and we use a very sophisticated set of equations. And we can solve that, and we can get very, very accurate results. And there's actually different levels of fidelity within that, right? So we can go inviscid, which means there's no viscosity, and maybe that's good for finding shock waves. And then we can add viscosity. We can add the boundary layers. We can add more levels of complexity to this, and get to higher and higher fidelities, higher order methods. And that gives us much better results. And maybe at some level, eventually you actually have wind tunnel testing, and wind tunnel testing is pretty much as close to truth as you can get without flying an actual airplane. And so that is a really high level fidelity. So we can mix all these different information sources. And so multi-fidelity optimization is a way to mix these information sources to optimize better. So in the optimization process, like if I were to take the most expensive type of data source, which would be wind tunnel testing, if I needed to wind tunnel test every possible way we could build an airplane, it would literally take forever, right? It's just not possible. And that's why we have analyses models, right? So I can have the simple model that's a simple line, and I can use that. And I can fit that in with my CFD data, and I can fit that in with my wind tunnel data, and I can fit that in with all the other data points I have, and I can use those together. So I can use, when I want to search a little more, I can use the lower fidelities, the cheaper things. And then I can also augment that with the more expensive data that I do have, or the more expensive analyses I have, and combine this in a way. And so I kind of get the best of both worlds. I have the accuracy of the high fidelity, and I have the speed of the low fidelity. And that allows us to solve optimization processes that are not capable with just a simple low fidelity that would just maybe not be quite right, but also not have the cost of a high fidelity that may take forever.
Mhm. And what is considered a small UAV, and what are the challenges associated with designing small UAVs?
Yeah, so look, from my background, I was always an RC airplane nut. So this is kind of something that I really enjoy. So small UAVs are anything, we usually classify that anything under 55 pounds. And there's a few challenges, and they're different than regular aircraft design. And I'm going to pull out a few of them. So the most basic one is Reynolds number. So Reynolds number is the ratio of your inertial forces to your viscous forces. And so if you have very high amounts of inertial forces, like you'd see in like a supersonic airplane, viscosity is not a huge factor, as much as a small like butterfly. Viscosity of the air is very prominent for a butterfly, but they're not very strong. They're not moving very fast. So with an RC plane, it's very similar. When you compare things, or a small UAV, it's very similar to what you'd, that comparison between like a 747, just very high inertia, a lot of energy in that flow. The viscosity of that small aircraft does dominate and change things. So that affects how the propellers work, that affects how the wings work, and so it changes how the stall models are, and it changes how the propellers perform, and so that has to be accounted for. So that's the most basic one, is that the same models that work at a larger scale sometimes don't work at the smaller scale. Now, the other factor that I think is really easily overlooked is the construction. So for airliners, we have a very nice way of designing them. We know what the wings, the ribs look like. It's a very standardized process, I think, at this point for many vehicles. And some people argue like, well, we have a new construction technique that we're working on, and that's fine. But there's not the breadth that there is in UAV design. There is a lot of different ways and a lot of construction methods that you can design a UAV, and they all work. You can use wood techniques. You can use carbon fiber. You can use foam. There's a lot of different composite work you could do. And so factoring all those into the construction does make it really difficult to figure out the weight. And the weight is a very necessary part of the vehicle design, because you don't know how much it weighs. You don't know how much lift you need to make and how that's going to work. So that's a big part of this. But another thing that people really overlook is that small UAVs are fragile, right? So the loads that I would size a full-scale aircraft to are not the same that I need to size a UAV to. So for example, I could never accidentally drop an airliner. Like, how would I even drop an airliner, right? It's not going to fall off the back of my truck, but my UAV might fall off the back of my truck. And someone's gonna crash it a little bit. You don't crash a little bit, an airliner, that's a major accident, but people will, fly a UAV maybe into a tree. Might happen. So they need to be able to handle that sort of abuse, and so that's a little bit different. So the airframes tend to be not as overly optimized for the minimum set at a weight, but it does change the entire design process, and it changes how you would look at how you do that.
And what are some of the alternative energy aircraft concepts that you're currently looking into?
So in the past, we've looked at a lot of different concepts. Right now, I'm spending most of my time on electric concepts. And yeah, like for example, we've done fuel cells, hydrogen, some mixed cycles, and a lot of different types of looking forward. But I think electric aircraft in the future will kind of be the way things are going. And it does change how you look at aircraft design and more so the business plan. So I think that's another thing that a lot of folks kind of gloss over, is that for electric aircraft, you're not going to go super long range. You're going to go short range. It's just the nature of how the energy densities work out. So with shorter ranges, then you can start being more creative and say, well, what sort of things can I do with this shorter range? And is this really interesting? And it ends up being very interesting, actually, because maybe you start changing some things out and reorganizing how you do transportation around a city or in other short range applications, regional transportation. And all this is green and clean. And so I think that's really exciting. And so we work on this. It's at the forefront of what we're doing right now in our lab and in my research work.
Mhm. And could you talk about your experience in the aerospace design lab?
Yeah, sure. So I didn't go through this in my bio, but I did my PhD and my master's with Professor Juan Alonso in the aerospace design lab, which I'm still working with in the postdoc, which is a little bit different. But the reason why I stuck with this lab and why I like working with Professor Alonso is he gives you a very long leash, right? So he allows you to explore and try a large range of different aspects. So within the lab, there's aircraft design is a very broad field, as I mentioned before, because we need to be proficient in a wide range of skills. That allows us to each kind of go in certain areas. And so within the lab, my lab mates are working on totally different projects than I am, which is great. We get a lot of really interesting things. And sometimes the collaborations can be really interesting. But with that, you do have to become a very independent researcher, which is, I think, really good for my growth long term. I know that I can be an independent problem solver. I can find, if there's a problem, I will find the solution. I will figure it out on my own. I will find the way through that. And that's sort of the nature of it. I think it's unfair to ask Professor Alonso to know everything and he knows a lot. He's incredible. He knows, everything from basic, mathematics that are just beyond what I know to, CFD structure. So he knows a lot, but the intricacies of specific research are outside of him. But within the lab, we do a lot of CFD research, aircraft design. We've done a lot of things that kind of assist that. So there's a little bit of push towards a little bit of AI that's mixed in there. And then as far as the culture of the lab, we have a really nice culture, and that's one of the reasons why I am really happy and sticking around there. It's very respectful. Folks are helpful, and it's really fun. All the people I work with are great. So it's a good time. Really like it. I'm gonna also give you a piece of advice here. If there's any people who are going to go to graduate school at some point and you're interested in the lab, go talk to the students, talk to the professor, but professors will always give you the rosy answer and the students will give you the truth. So if you talk to the students and the students are happy and they like what they do and they're honestly really like what they do, then I think, and they're happy with both the research and their life, then you found the right place. So that's my advice for people who are looking for school.
Mhm. And what has been your toughest accomplishment so far?
So at Stanford, we do a thing called quals for the PhD program. And I'm sure a lot of people are like, well, the PhD is hard. Well, it's not really the PhD that's the hardest. It's actually just the exams. We have a set of exams that it's basically like every final exam in aerospace in 1 week. And what you do is you sit in front of a group of professors and you solve final exam problems on a board. And they give you some really wacky things that you just never thought of. And you don't have a cheat sheet. You don't know what you have to know all the equations. So you have to memorize all the equations that you might possibly ever need or be able to derive them. And you have a very limited amount of time to have these equations memorized, apply them to something absolutely crazy, and maybe even have to be able to solve it in multiple ways, which had happened to me, that there's more than one way to use this and solve things. So that's the hardest challenge, I think, for a lot of people who go through Stanford AeroAstro is the quals process.
And what is a big milestone that you're looking forward to in your research?
Yeah, so we talk a lot about aircraft design, but that's really just part of my research right now. So I'm really interested in how engineers design and what they sort of do. And I see there being a big change in the next few years. So right now there's optimization processes, and they're really good at finding what the optimum solution is. But a lot of times when you start a design project, you actually don't know what you're trying to design, and that seems really vague. You would think you'd know what you want to design. So what we can do is we can combine aircraft design methods. So these analyses, we have multiple fidelities, of course, we just talked about. But we also have some AI tools, and we can take the AI tools and we can explore those data sources, and we can see what the possibilities are. So what I would really like to do coming in the next couple of years is combine these two and explore the design spaces. We have these really cool electric vehicles and other energy vehicles coming up, and we really don't know how to design them. This actually is a fundamental problem. Folks, this is a new technology and we don't know how to utilize it better. So if we can find better algorithms to search the design space, come up with new ideas, and help us design aircraft, that'd be really awesome. So that's the next big milestone I'm looking for.
Mhm. And to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Yeah, so I actually have two things that are seemingly incompatible. So the first is when you go to, eventually you're going to go to undergraduate and you're going to study. And I think when you start that study process, you're going to be faced with they're going to almost boring classes. We called some of them the gauntlet when I was an undergrad, that were the fundamental engineering classes. But even to get to the gauntlet, you have to take math, you have to take physics, you have to take English. But really, you should like those classes and you need to be really solid in them. So and then when you get to the gauntlet classes, the statics, the dynamics, the fluids. So all those core engineering skills, you need to be really good at. And it helps you do a couple things. You have to learn how to become a good problem solver, and you need to be able to communicate those results that you just solved. So that's why English is important.
Mhm.
So what's also important there is that you're going to take these classes. They're not going to be your favorite classes because they're not aerodynamics. They're not talking about airplanes. You're talking about a box sliding down a ramp or a lever or something, that's like totally arbitrary. But if you're going to do something like this, and you should keep the same mindset, is that if you're going to do something, you should do it right. You should learn it. You should learn it really well. And the reason is later on, you may need those skills. And so the second piece of advice I have, so the first is get really solid in the core skills of engineering, is that the second is you have those building blocks. Now keep your eyes open to what's in the future. So take a wide variety of classes. At Stanford, I took stuff all over the place. I took PE classes. I took a class in emergency medicine. You should just take a lot of different classes and see what's really interesting to you. It could be outside of aerospace in engineering still. It could be in anything else. And the idea is to keep your mind open, because you never know what, as either a human being or as a professional, what is going to be either interesting or useful to you in the future. And so you built these fundamental core skills, you're solid in them, you know how to solve problems. And so you can still use some of the intangibles that you're going to pick up in these basic classes and apply them, learn new skills. And then this same set of ideas applies to your life and your job later on, right? Build fundamental skills that help you solve problems and do things, and keep your eye open. There may be a really cool opportunity that you're missing if you just keep your tunnel vision that you just have to do the bare minimum. But if you find something really interesting, don't be afraid to explore it. Don't be afraid to look at something new and exciting that you didn't imagine was going to be on your path.
Mhm. Well, thank you for joining me, and thank you for letting me interview. That was great.
Yeah, happy to help. All right.